All right, so yeah, welcome to this recitation. It's a small class, just a handful of people, just two of you. So let's get started. So recitation, in case you haven't, in case you didn't participate in the first one, recitation is essentially me going through selected questions, and we're gonna write out the answer rigorously, and this way we'll train students to essentially know, not just the final answer, but also the intermediate steps in the middle. So with that being said, that's the purpose of recitation. Today, this session is going to be about sufficient statistics. So let me start by writing down the topic. Sufficient statistics. Let me just walk through the idea first. The sufficient statistics is essentially set up like based on the following motivation. So let's say you have approach one. Approach one is you can observe data. So I'll say you observe x1, x2, x3, to xn. Let's say this is your random sample. So if you observe the data, you can do a lot of things with it, right? You can compute the average, compute the variance. You can do a lot of things with it. The approach two is you don't observe data, but you can like guess some functions of the data. So we're going to call that t. So this t, it's technically speaking t of x, but this t we're going to define that as textbook notation is a phi of x1, x2, all the way to xn. This is like a function of the data, and based on these two approaches, you can kind of guess that the first one is probably going to be more general, right? Like you have all the information, you observe all the data. That's the best you can do. Right, so if I intuitively, you can kind of say that, you can kind of guess that, okay, approach number one is probably better. So that's intuitively, that's what we mean. But it turns out that you can actually pick this function t, such that it can carry all of the information from your data, perhaps without observing it. So that's kind of the idea here. So the idea is the following. In general, one is better. Observe data, you calculate it, done. That's all the information. But if we can choose a special function t of this phi thing, such that it carries all the information, then we say, t is sufficient. So that's kind of the idea here. And in practice, in terms of problem solving, the good thing is we don't usually go from definition, all right, because that's slightly more difficult. So what that means is we actually have this nice theorem called Factorizing Theorem. So I'll write that down, Factorization Theorem. And when we solve problems, we're gonna take full advantage of essentially the statement in the theorem, which I'm gonna write in a second. And that's how we carry out the analysis. So let me just directly write out the theorem. So just like MLE, right? You start with your data. Suppose you observe data, x1, x2, all the way to xn. That's your data, and it's IID from some sort of distribution. Usually we call that fx, and the theta is essentially the parameters of the distribution. So let me write out footnote, this is going to be some sort of distribution, right? This F, this X essentially you can consider as your data. This theta is going to be your parameters. And you observe X, right? So you probably won't know what this distribution is. So technically speaking, this theta is unknown. All right. Now here's the theorem. The theorem says that this function t, and we're gonna be consistent with the textbook notation. So there's gonna be a function, we're gonna call that R, x1, x2, there's a comma, all the way to xn, is sufficient statistics if and only if, and we're going to write the following condition. So for all values in x, as capital X is essentially your data, x1, x2, all the way to xn. This is n, so that's in, you can kind of think of as in n dimension. So when I write this boldface R, that's a boldface R like that, that's a real number. And this n just means you have n dimension, because here you have, this is n here. So that's what this notation means. And this means this is an element of this. So that's kind of what's happening here. So for all the values that you can take essentially in the set, right? The joint likelihood function, so we're going to write it out, fn x theta can be written as a function of x times a function of r of x and theta. Okay, so this is mu and this is nu. Okay, so this mu is nu. These are Greek letters. Of course, they are not like completely random, right? Like they're conditions. So we say where mu and nu non-negative. Oops, sorry, non-negative. And then the key condition here, the key premise here for this first function mu is that it does not depend on theta, right? So you do your work, and end of the day, if there's a theta somewhere here, okay, then that's wrong. All right. So whatever this component is, theta cannot be in there. Theta has to be here. All right. So that's the first condition. So we're gonna write that down. We say mu is not dependent on theta. All right. And the second term, obviously, you can depend on r of x and theta. All right. Oh, let me open my screen. So, all right, there we go. Okay. All right, and then if this is the case, and that's how you break them apart, right? You factor them into different components, then you can call this Rx your sufficient statistics. All right, so let's write that down. Where this R of x is sufficient statistics. So let me pause. Do you guys have any questions about this? Good. Give a thumb up if you're good. Good. Oh, awesome. Cool. All right. So again, that's a theorem. It's extremely important. And next, we're gonna look at a couple of examples. Essentially, allow us to directly use this theorem to come up with answers. So let's continue from here. All right, this next example is going to be a standard textbook example. It's going to be, I believe, 773. Okay, so it's a standard setup. suppose you observe data x1, x2, da 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 da, and you can say this random sample from some sort of distribution, and it tells you what distribution is. So let's write it out. This is f x. Theta is a parameter, and the distribution is essentially defined as theta x theta minus 1 for 0 less than x less than 1, and this is 0, this is else. All right, so let me just put a remark here. This notation is textbook notation, essentially saying if your range, if the x, right, the x is your data, right, in this distribution, falls in the range of 0, 1, then your distribution function takes this form, theta x theta minus 1. If it's not in this range, right, else, then it's 0. So this can also be written out as indicator function, and we're gonna define what that means. So this is a remark. An indicator function of some sort of input, let's say alpha, right? This alpha, you need to specify what range that you want in this indicator function. So I need to be a little bit more careful here. I need to say, I'll give it a range, right? Let's say alpha is positive. So what does it mean? This means if alpha is positive, this gives me 1, all right? Otherwise gives me 0. So what does otherwise mean? Otherwise is the complement of the set alpha greater than 0. So it's alpha less than or equal to 0, right? So when I say else, I meant the complement of the first range, the range defined in the first line, right? So this alpha less than or equal to 0. And if that's the case, your function is 0. So that's the indicator function means. Now, consistent with the notation of the course, which professor used the indicator function, we're gonna try to rewrite this f using indicator function. So what that means is I can actually write out. So here we say using indicator function, f is actually theta x theta minus 1 times indicator function. You can essentially say something like this. Or you can write a set here. I've seen some notations like that, or you can write x in that if you want. Some people write like this. X is in 0, 1. They're essentially, referring to the same story. So if x fall into that range, 0, 1, then we have theta x theta minus 1. All right. Otherwise, this function is 0. So that's kind of the idea here. And the reason this is important is because if we don't do this, you're going to see that when we use the factorization theorem, something's going to go wrong. All right. So so that's why we kind of write it in like one line. Don't write like the bracket way. Maybe it's like an easier way to interpret. So with that being said, that's a problem. All right. It's a standard setup. We have all the pieces of information. We have the data. We know the distribution function. We have all the pieces of information. So now some questions might be worded a little bit easier. They will say like, show this is the sufficient statistics. I will tell you, show this. Some question will just say, find the sufficient statistics, right? So sometimes people get confused because they see that the first line of answer, it says, show something is sufficient statistics. And then the question is like, find sufficient statistics. So then people get confused, like, how do I know that's the sufficient statistic if I don't really solve it? Well, when you see solutions like that, usually they work out the answer first, and then they come back up to write this line. So usually they write out the answer first, they come back up to write this line. And I'll show you what that means in just a sec. So okay, so let's solve sufficient statistics. All right, before you know what it is, you have to solve it, and then you come back to write the final answer. The first step of finding sufficient statistics is to look at what your let's use a theorem. All right, so it's look at this guy. All right, so what is that? That's the joint likelihood function. All right, so let's write that out. All right, so say observed data, you can write out Fn x theta, and what is this? This is technically speaking, let's follow definition. It's pi I from 1 to n f x I theta, right? You have n terms. How do I know that? Because in the data here, there's n. Maybe I should write out here just to be clear. There's n here. So that's why we have n terms here. They multiply each other. Each one is a density function, and their IID, right? Okay, so now if I don't have the indicator function, I might tempted to just write something like this. If I don't have the indicator function. Now, if you do that, you might like run into a small problem. So it's so you're probably better off leave the 1 in there. You know, so so let's see. I think you let's stick with this. So x in 0, 1. All right. Okay. Now we have all the pieces of information. Let me not forget this rounding index I. That's important. And we can essentially work on the math. So the n terms multiply together. So what is it? Let me write it out very clearly. So that's x1, theta 1, right? Because I set at I equals to 1, I plug in here. That's my first term. And then I do the same thing, theta x2, theta minus 1. And I do the same thing, x3, theta minus 1. Make sense? I can be 1, 2, 3 all the way to n. We write all of them out, all of them multiply together. That's the product of n terms. And obviously, you know, don't forget this. All right, so if you look carefully, you notice that this indicator function actually ensures that all of your data has to be essentially between 0 and 1. If you have one of the guys to be like, say, -3, then your entire function is 0. All right, so that's what this indicator function means. And you have n terms, right? N theta. Theta doesn't change. So you write them together, that's theta to the power of n. All right. And here, what we have left is x1 times x2 times xn to the power of theta minus 1. And within the parameter, I can use the product. So that's I from 1 to n, xi. Outside of parentheses, I have the power term theta minus 1. Right. So now we have essentially rewritten your joint likelihood function, right, of this problem in this way. Okay, so now it doesn't seem like we can continue from here, right? It kind of like gets stuck here. And when that happens, usually it's a good spot to check if you can directly apply the factorization theorem. Okay, so that's kind of a story. So what do I mean by that? You go to the factorization theorem, you say, okay, I need this piece, and when I write this piece, I need to make sure R is not in there, theta is not in there. Okay, so let's shoot for that first. So you know, you look at this, right? It seems like X is in here. It seems like theta is in here. But then this piece, X is not in there, right? So the easiest way is just to call that mu. Okay, so if I may, here you can essentially say choose mu x to be theta n. Now, notice that this x does not have always to be in there, right? It's kind of like optional. The key point is, as long as this mu of x does not depend on theta or your sufficient statistics, then you're good to go, right? So this mu x can be anything except for sufficient statistics and your sorry, let me be a little bit more clear. It's actually this part, and here maybe I should be a little more careful of this data. You can actually choose this to be theta n. I think let me check my notes. I think maybe there's a small issue here. Let me just pause for questions. Do you guys have any questions about this part? Let's see. Any questions? Okay, so let me double check the problem. Yeah, it seems like the sufficient statistics is chosen as a product term. So let me write that down. This is to choose r of x to be this product term pi I from I to n and xi, and the new term, which is a combination of sufficient statistics and theta. So that's the new term. This is essentially the second term, xi theta minus 1. Let me check the condition of the factorization theorem to make sure I don't miss anything. Okay, I made a small mistake here. This is not theta. This is to be essentially 1. And then this new function actually, sorry, let me write this. I am going to move this here, and then I am going to move this guy here, and I'm going to put theta in here. Because the first function, mu of x, cannot be dependent on theta. So that's kind of what's going on here. So let's just recap, and let me just restate this to fix my mistake. So let's start. So what we just did was we start with the joint likelihood function, right? We have this f that's given to us, and we use this definition to work out the joint likelihood function, and it looks like that. And you work out the math, you keep going all the way to the end, you get something like this. Now, when you are in the end of this equation, you need to think about how to apply the theorem. And the theorem essentially tells you all the conditions of the moving pieces, right? The mu, the nu, the r of x, that sort of thing. And it comes with its own premise. So premise is mu cannot be dependent on theta, right? So that's a mistake I made in the beginning. I somehow write theta in there, so that's wrong. It actually just be 1. It may or may not depend on x, that's okay, but theta, it can't, right? So in this case, we don't really have an individual function of x, right? Like everything else is theta in it. So you can imagine there's like a fake 1 here, and then you're just gonna call that mu. The rest of the function, you can kind of think of into a function of x or theta. The function of x is just this part. Theta is here, so we don't really care about that. The x is what we care about. And that part is going to be sufficient statistics. Okay, so once again, the idea is if I can write my joint likelihood function in this way, which can be broken apart into all these pieces, then this Rx is sufficient statistics. Okay, so when you're there, so once you have this answer, then you can come back up. You say, show, I can erase this. You can say, show this product of xi is essentially your sufficient statistics. Does that kind of, so let me pause. Any questions about this? Good. Give a thumb up if you're good to go. All right, awesome. Cool. I see one thumb up. So I'm gonna assume that you guys are okay. All right, awesome. So let's take a look at another problem. Let's see. The next problem on my notes is uniform. Okay, so let's continue from here. So next problem is example, 7.7.5. And this example is sampling from uniform. It's the exact same setup. Okay, so suppose your data x, x1, x2, all the way to xn. This is a random sample from uniform distribution. So this is a random sample from uniform. And with the parameter 0 theta, I think sometimes people write like this, but it's a 2 parameters from it's an interval of your uniform distribution. And you know, you can assume that theta is unknown. And also, whenever people write interval like this, 0 theta, it's implied that theta is positive. Okay. I think some students have problem with that. Let me know if that's a problem, because that's very basic stuff. You know, when you write a set, it's like from left to right, it's like small to large. No one writes the opposite way. Okay. So I actually don't have to write this. Like if you give a bracket 0 theta, it's implied theta is positive. Theta cannot be -2 in this case, right? So yeah, so that's kind of the idea here. And this time the problem actually do us a favor, right? Tells us let the Rx. So let's write that down. Let Rx equal to max x1, x2, xn. Okay. Do you guys know order statistics? So let me just put a remark here. So this can actually be written as x parenthesis n. Okay. So if your x is 1, 2, 3 all the way to n, and you take the maximum, you can write it as parenthesis n just to simplify a little bit. And the reverse is also available for us for simple notation. So note, I'll put a remark. So remark, order statistics, the notation is the following. This is a notation. X order n, or x parenthesis n, this is max of all of the x. X1 is the minimum of all of the x. All right, so that's just the standard notation in case you don't know that. In this case, we're going to use the first one. So I'll just start writing x parenthesis n. And what that means, it's the largest number, the maximum number of all of the data, x1, x2, all the way to xn. All right, so the goal is very simple. Because the question asks us to show this x order n is your sufficient statistics, all right? So show t equals to max x2 all the way to xn. I can of course write out as order statistics is sufficient statistics of theta. All right. And the PDF, don't forget the PDF, it's a uniform. So let's write that out. This is fx theta. Theta is a parameter, and 1 over theta. So this is the range for 0 is equal to x is equal to theta else. And once again, this can be written as what? 1 over theta, indicator function, the range is this. All right. Okay, so let me pause. Any questions about what I just said? That's a problem. Hopefully all the information is clear. And I think once you have the information clearly written out, and of course, assuming that you know the theorem, you should have an idea of what to do next. So once again, according to the theorem, we're looking at what? A joint likelihood function, right? So this is the problem. Next step is write out the joint likelihood function. So we know that. Now we're going to do, so we say first, write joint likelihood function. Okay, so fn x theta, it's like 1 over theta to the power of n, right? But then notice that you have an indicator function, so you shouldn't miss that. So we're gonna say let's stick with the definition. So this is product, which is a capital pi. I is your rounding index from 1 to n, and the PDF theta. And don't forget that you have this guy here. That's your range. If one of the x falls out of the range, the entire function goes to 0. Okay, so that's what it means. This time you're gonna notice that this indicator function is gonna come in handy. So once we have this, technically speaking, there isn't really a whole lot we can write. 1 over theta is 1 over theta. There isn't really a whole lot of calculation. So what's gonna happen is we're gonna essentially write it out to be 1 over theta to the power of n, your indicator function, that's your range of support. And once you write it out, you can just write x theta. Okay, so now we're here. What do we do next, right? The next is obviously to apply factorization theorem, but the question is how, right? If you recall from MLE, we start with the same thing, right? Joint likelihood function. But then based on the setup and the nature of this function, we don't really want to like take partial derivative or anything like that, right? We use the order statistics to find the MLE. So it's kind of like you can kind of think of it as like the same story here. So the first thing you need to realize is if one of these xi's, so if one of these guys is 0, if one of these guys is outside of a range, then the entire thing is 0. Okay, so that's covered in this part of the function, and we need to preserve that information. Okay. When you do the when you're trying to define the pieces for the factorization theorem to apply that, you need to preserve that information. So because of that, we should just consider all of the x within the range, and we're done. But otherwise, it's 0. Does that kind of make sense? So that's why I said indicator function will come in handy, right? So with that being said, now you can kind of just jump in, right? Because u of x can be anything you want. Right? We've seen last problem, u of x is 1, right? So that we don't really care that much. The first thing we need to look for is your new, right? So find new. And what's new? New is r of x theta. So find this guy. You can kind of so now you don't really have a whole lot of like this is the only piece that you have, right? You don't really get a whole lot of other choices. So you can kind of define essentially this new. So you can define this new by some sort of Rx theta. Now I'm being a little loose here on the notation. Technically speaking, this instead of writing it this way, I should really be writing it as t theta. And the reason I'm writing that is because here in this statistics t here, it's actually a moving piece. It's actually a moving piece. So that's why I'm using this small t here. It's because we have xi all the way to xn's, okay, and they're moving pieces that help us define what is Rx is, which is your sufficient statistics. So in that case, we know that it goes with some sort of, it goes with some sort of 1 theta n, but then the problem is what is going to be inside of this indicator function. Well, since you have a t here, right? We have a t here, so you can kind of guess it's some sort of t. But then this t, since it's representing some sort of x, right? Then that's why we have to stick with this range. So you can write t less than or equal to theta, all right? So let me pause. Any questions about this part? I know it can get confusing. So it's important that we tackle this. Good? Give a thumb up if you're good with this part. Good, awesome. I see a thumb up. Okay, good. Okay, great. So now essentially your joint likelihood function, right? This f of x. So we can essentially, so thus you can say thus this f of n x given theta can be written as essentially this part. And then if you choose u of x to be 1, then this is essentially u of x times nu t theta, where this t is sufficient statistics. Okay, let me double check my notes, make sure I'm not missing anything. This t is and then here let me just make sure I'm being very clear. This t, if you want to take it as like a kind of like a fixed number, right? Because we talk about this moving part, right? So if you want to choose t as like a fixed number, then you need to make sure that you pick the largest of all the data you're given, but then they're smaller than theta, right? Because that's essentially because that's essentially like the minimum range of theta, and that kind of ties up to like the idea of MLE. So so here if you want to so here let's be a little bit more careful. So here this t should really be max of x1 x2 all the way to xn, and it's really just x order n. Okay, so then you can come out and say, that's what we're trying to show. Okay, and the reason is because of the analysis in this part and this part. All right. So from this part, we're looking at essentially an array of x, right? x1, x2, all the way to xn, and they're moving pieces, right? And theta is sitting on here. So if I write this out, let me use a different color. So what's going on here? So this technically speaking is 0 x. If I'm gonna use order statistics, let's say x order 1, x order 2. When I say x order 2, it just means that if you order them, this is the second in the rank, all right? So that's what x order n means. And then we have x3, x4, all the way to xn. And then don't forget that here you have a theta, right? So since they're order statistics, then I can write out the sign. So it goes something like this. Okay. So then the question is, okay, what is the x here that represent the closest information of theta? Well, it's this guy. So in other words, the question is asking you, what is sufficient for us to describe this theta? Okay, so in the uniform distribution, let's draw that out. Uniform distribution looks like this. Okay, and according to the problem, that's going to be theta. Sorry, that's going to be 0. That's going to be theta, right? And then you have your theta line up like this, right? 0 is on the very left, theta is on the very right, and that's your theta in between, right? You have a bunch of dots, they're continuous. Then the question is, okay, what is this theta? What point do you pick so that you can describe theta? The best guess of theta that you can pick. Well, I'm gonna pick the largest x, the largest x here. So this is xn here. So that's the idea. Make sense? So questions about this part. That's kind of like the essence of the problem. That's why the problem says show that x order n is your sufficient statistics. That's a problem here. Good? Give a thumb up if you're good. Awesome. Okay, cool. Let's jump ahead and talk a little bit about asymptotics and the confidence interval. So let me open up a new page. Okay, so let's start talking about this. So this problem, so next I wanna essentially walk through like a whole framework of from all the way from like central limit theorem all the way to like when you write out the confidence interval. So let's get started. So let's say you observe data, right? So let's say you observe data x1, x2, all the way to xn. They're of course IID, and I'm going to make it very simple. Let's say they come from normal mu sigma square. So if I write like this, they're not necessarily standard normal, right? They're just some normal distribution. It doesn't have to be 0, 1, right? So mu and sigma square. We all know central limit theorem, right? The moving pieces inside of a central limit theorem is essentially your x and your expectation x and your variance of x bar, right? So let's write it out. So first, x bar, we need to find mean and find variance. Okay, so mean is essentially expectation, right? And let me just define. Okay, so denote x bar as 1 over n summation I from 1 to n xi. Right. Sometimes people write a notation like there's an n here, but as long as they define it to be summation of everything and then divided by n, then we're good to go. They're talking about the same thing. So I'm just going to omit that just to avoid confusion. Now, expectation of something is essentially the mean of something, right? So here's x bar, so then it's the mean of x bar, right? It could get a little bit mouthful, but stick with the notation. So what do I mean by that? Well, let's plug in the definition. Definition is what? It's here, right? So let's plug that in. 1 over n summation I from 1 to n xi done. Now 1 over n is kind of like a constant, right? It's like a factor, right? So it doesn't matter. I'll put that out. And then inside we have expectation of the summation term. And now the summation terms, there's no like cross term or anything like that, right? It's expectation of, so if you have expectation of x plus y, then that's equal to expectation of x plus expectation of y, right? So if that's the case, then I can very well just factor this expectation inside. So then I'm going to have expectation of xi, right? Now you're going to notice something interesting, right? Because they're IID, right? Here we tell you that they're IID. Then, technically speaking, these n sums are really just the same number. So I can actually write 1 over n mu, because it tells me that the average of all these x are mu. So in other words, the trick here that we use, let me put this arrow to this equal sign here. So the trick here we use is expectation of x1 equal to expectation of x2, equal to expectation of xn equal to mu. And since there are n terms, right, 1, 2, 3, all the way to n, then you have n mu. Now the lucky thing here is n and n cancel out, so you end up just mu. So the conclusion here is, if you look at the average of the average, it's just your average. So that's essentially what this statement says. Okay. So we're done with the first one. Now we're going to move on to the second one. So variance of x bar. All right. And we plug in definition, right? That's the first step. So variance of 1 over n summation I from 1 to n xi. The first thing we do is we pull 1 over n out. It's a constant, doesn't matter, we pull it out. But when you pull it out, because it's variance, there's a square, okay? So what I mean by that is the following. 1 over n squared variance summation I from 1 to n xi done, all right? Now, here's a tricky part. 1 over n squared stays the same. By technically speaking, if you want to use a formula, you want to use a definition that you learn from probability theory course, this variance, like the variance of x plus y. Now, technically speaking, that's the variance of x plus variance of y, and then there's like a covariance term here, right? But then since they're IID, then this guy goes to 0, so it's gone, right? So technically speaking, not everywhere, but in this situation, I don't actually have to write any of this stuff. All right, because they're IID. Now, if we agree with that, then I can just pull the summation here and move the variance inside, and will give me this summation of variance xi. I move the variance inside. And the reason I'm allowed to do that is because all the cross term, the covariance term, they all go to 0. All right. So this makes my life much easier, and we can use the same trick, right? So from here we use the same thing. Variance of x1, but technically speaking, that's equal to variance of x2. Same thing with 3 all the way to variance of xn equal to what? The problem says is this guy, right? So they're equal to sigma squared. So now there are n of them, then you have to use, n times sigma squared. So this gives us 1 over n squared, n sigma squared. And then obviously this cancels out, right? So now you're left with sigma squared over n. So now this says a little bit interesting statement than a little bit more interesting statement than the expectation of X bar. So the variance of X bar, so essentially this conclusion here is the variance of your sample mean X bar is your sigma square, which is the variance of your original distribution with a factor of n, right, over a factor of n. And in other words, it's kind of consistent with our intuition, right? Like if you have more and more samples, then your sample average is gonna get more and more accurate, right? That's kind of the idea here, and that should make sense. Intuitively, that should make sense, right? If you have a class of 10 students and you take an exam, the average is gonna go all over the places, right? But if you have a class of like 100 students or like 200 students, then you can kind of expect that you take the exam and the average score is probably much more stable than the previous class with 10 students. That's kind of the idea. But the idea is just an idea, right? But how do we formulate that, right? How do we rigorously write out what do we mean by more stable, that sort of thing. So that's a concept when we start to introduce asymptotics, and later on we're gonna land on confidence interval. So here I don't want to hold you guys too long after 10, so let me just say here. So by central limit theorem, you can kind of write like this. I'm going to write out step by step. So X bar minus mu, this is technically speaking converge asymptotically to n, which means normal distribution, means 0, and your sample variance. So technically speaking, I should write this. All right. And now this is going to give me a slight problem. And the problem here is that this variance is vanishing. So when we say vanishing or degenerating or goes to 0 or anything like that, it means this. So degenerating, this means when you take the limit of n goes to infinity, this sample variance, right? This I'm just copy from here, right? So the sample variance goes to 0, and it's not goes to 0, it's exactly 0, right? Because you take the limit. So that's going to be a problem. How could I have a normal distribution that the variance is 0? That doesn't make any sense. If that's if that's where like normal distribution should look like this. If your variance is 0, then technically speaking, you don't get this curve. Then you get something like this. We don't want that, right? That's not gonna give us any information. So because of that, we want to essentially move out that n and move to the left-hand side, right? So what I mean by that is the following. So here, I should really be doing this. First of all, I'm going to get the n out. But when I factor n out, notice that since it is the variance term, then when you take it out, you need to take a square root. Okay, that's because of the PDF of the normal distribution. So now the square root is out. I just move to the left-hand side. So now, thus, move to the left-hand side. So square root of n x bar minus mu. This gives me normal distribution 0, 1. And that's the central limit theorem. That's the golden idea of what we're doing here. Well, that's terrible. Let me use a different color. Okay, so that's kind of the idea here. Now the last piece of statement I'm going to give you is a confidence interval. So the reason that we have this is because we can write out the confidence interval. So you can kind of say something like, we know that normal 0, 1 is like 1.96, right? Like that gives you like 95%, right? Something like that. So where does that come from, right? So it's essentially saying, so you can kind of say, so let's see. So you can kind of say, what is it's this guy here, right? So you can kind of say, probability of this guy, and within the some people say rejection region, some people say critical value, but you get what I'm saying, like the rejection cutoff of the region for your data to fall in to achieve that probability that you want. So because it's normal 0, 1, so I'm not going to trick you guys, so I'll just directly write it out. So you can kind of think like 1.96, this is positive 1.96, and this will give you whatever, 95%, you know. And these values essentially come from the table, or come from R or Python or whatever program that you want to use. Is perfectly fine. And what will that give you, right? So this is kind of like the source of the idea of confidence interval, right? So let me write it in the middle. So this is what we want, right? So the goal here is, what is the confidence interval such that we can achieve this? So that's kind of the idea here. And how do you do that? So what you want to do is you want to break this apart. So let's write it out. So this is exactly what this is 1.96. You want to divide it by square root of n. Here you have 1.96 divided by square root of n. And then now you have x bar minus mu, something like that. And now I'm going to move this mu here. So we're going to have something like this. Right? So I'm not doing anything crazy. I'm just moving all the pieces out from the middle and put it on the left and right hand side, so that in the middle is left with x bar, right? This is x bar. So now you get the idea, right? So what's the confidence interval? You know, what's the upper and lower bound? In order for us to achieve this 95%, why is, you know, this is it, right? This is where it comes from. Okay, so we're a little bit past 10 o'clock. Let me pause here. Any questions about this? Good. All right, awesome. So yeah, so we're a few minutes behind 10 o'clock. I think that's also because in the beginning we gave a few minutes to see if somebody show up, which is okay, perfectly fine. I'll stay here for more questions if you guys have. If not, you guys are free to go. Thank you for listening.